So this is Level 2 Coding and Data Analysis, and this is a video tutorial series on using Python for data science. And in this first unit, we're going to look at the Python library Pandas. And we're going to start off in our first part here with discussing what Pandas is for and when it's appropriate to go and use it. So in typical data science applications, we're often working with data that's quite complex. So something that is not just simply lists and tables of numbers. So we might therefore have things which are columns with different data types, so strings, categories, dates, as well as numbers. We might have missing or incomplete sets of data. We might have very large amounts of data and where we only want to process a very small subset of it. And quite often we're going to be looking at time series data. That's where you can think of each row in a table as corresponding to a set of values of different categories that all correspond to a particular value in time, a particular point in time. The Python package Pandas is designed to really help us with processing and dealing with this sort of data. So although NumPy is an excellent way for working with purely numerical data, in the real world our data sets tend to be a mixture of text and numbers and not just always pure numbers to work with. On the other hand, in many situations we can think about tables of data and where each row represents a set of information about an item, with the columns holding different categories of information related to that particular item. So this is the sort of typical use we have in a spreadsheet type of application. So of course spreadsheet programs such as Excel tend to get rather unwieldy when you're dealing with hundreds of thousands, if not millions of rows. So, and if we're dealing with data analysis questions where the functions we're trying to use on the data are starting to get quite complicated, more than you can express in a nice simple single line formula, then really we need a different tool to go and deal with this. And Python, and in particular Pandas library, becomes the tool of choice. So like NumPy and SciPy and Matplotlib, Pandas is not built into Python, nor indeed is it part of the standard library, but it's an additional package. But again, like the others, it frequently comes as part of a scientific Python distribution because it is so ubiquitous in the field of data science. So often I get asked about when we should be using Pandas and when we should go and use NumPy. And as a very rough rule of thumb, and there isn't really a simple answer to this, but as a rough rule of thumb, Pandas comes into its own when you're dealing with that kind of more complicated data. In many ways, Pandas is more powerful than NumPy, in the sense you can do everything you can do with NumPy, you can do in Pandas, but it's also more complicated, and it's a bit more resource intensive and sometimes slower. So as I said, as a rough rule of thumb, Pandas is better for when you have tables of data where the rows have each row contains different data types, so floats, strings, etc. When you can naturally think about the way you think about your data is you can give each column and possibly each row a label that isn't just simply a number or a range of numbers. And when you need to deal with missing or incomplete data. And in particular, Pandas is always the library I turn to when I'm given an Excel spreadsheet or I need to go and write an Excel spreadsheet, because it is super easy in Pandas to convert to and from Excel spreadsheets. NumPy, on the other hand, is going to be the preferred tool when your data is all basically of the same data type, particularly if it's numerical, like a floating point number. The data doesn't naturally fall into a table with rows and columns that can be labelled. So for example, if you're dealing with image data, that forms an array of numbers, okay, but you don't tend to think of each column in an image as having a different name. And when you don't want or you don't need the extra overhead of dealing with the more complicated data structures that Pandas offers, when you're really looking to get the maximum performance there. So Pandas provides us with essentially two core data structures that we work with all the time. That is the series and the data frame. Put very simply, the series can be thought of as just a list or a 1D array of values, but where each element in the 1D array or the 1D list can be referred to with some sort of label. A series you can think of as representing a single row in a table, in which case the labels that you're assigning to each value will be the names of the columns. Alternatively, you could think of it as each column, where each label on the row is whatever we're using to index that table to show which row we're on. A data frame is then like one sheet in a spreadsheet. It consists of a table of rows and columns. Each column has a name, and each row is defined by having an index. By default, when we use Pandas, it will automatically create an index for us for the rows using numbers from 0 onwards. But that's just its default action. We don't have to stick with its default index. We can change it, and we'll show later how to go and do this. Conventionally, we import Pandas as PD, in the same way that we import NumPy as NP and matplotlib.pyplot as plut, and so on. And we can then go and create series and data frames as we need them. In general, Pandas tries to be as flexible as possible when we pass it something, and tries to interpret what we've given it in the most sensible way to make either a series or a data frame. So for example, if we create pd.series with just a list of numbers, it assumes we want to create that as a series of numbers, and it gives them just a numerical index. So starting from 0 going up to 4. On the other hand, if we pass a dictionary into series, then Pandas will try to interpret the keys of that dictionary as labels, and then the values become the values of the series. So for example, here we've passed a dictionary into Pandas series, and we've created a series again with the same set of values, 10, 20, 30, 40, 50, but they're labelled with the keys, first, second, third, fourth, and fifth. We aren't just storing the numbers. You don't have to just store numbers in the series either. So for example, here I've created another series, again with the dictionary, but the values this time are the letters A, B, C, D, and E. So the series can store any type of data, and we can give it labels, and if we don't give it anything to use as the labels, it will default to creating it with some numbers. Notice that the series has a D type, just like a NumPy array, that specifies the data type of the values that are being stored. And just like NumPy, the relationship between the D type and the values that we're storing in them. Finally, we can think of a data frame as being a collection of series objects, each one representing either a different column with its own data type. We can then create a data frame from a list of dictionaries. Each individual dictionary specifies a row, and the keys of the dictionary become the column labels. Or alternatively, we can give it a dictionary of lists, in which case again the keys are the column labels, but now each list that's stored in that dictionary becomes the values for that column. So again, this is an example of Pandas trying to figure out the best way to represent the data we've got. So in this example here, I've created a single dictionary, but with lists of values. And you can see it's created a dictionary with the column headers A, B, and C, and then the values that we've specified in the array, in the dictionary as we passed it into the data frame. So we'll see later how we can load and save data frames to files as well. And that, of course, is going to be one of the key things that we need to be able to go and do.